Okay, Scott, why don't you start? The EOSs are a little more up your alley.
Okay. Yeah, so we started by, well, I think this is now more or less in chronological order to the discussion we had. So we started talking about equations of state and which ones we should use. People volunteered that they're using the Latimer's-Westy equation of state, and it's been used a lot of times elsewhere. And Jeremy's asked, well, maybe we should constrain the equations of state to observational data, in particular constraints by Neisser and LIGO. And so there was some discussion also about, well, we should constrain to what the kilonova signatures say too, but there were people saying that there's a great deal of uncertainty still in the predictions of the kilonova signal, that it's hard to give equations of state constraints. And then Luke talked about how the tabular equations of state are valid only up to about a second, and then you have to transition to, I think it was a second, maybe a little bit greater than a second, and then you have to transfer to a different kind of equation of state, and then nuclear burning occurs out to about a minute, but then you can assume that the material beyond a second, you can neglect neutrino absorption. And you can do this in a post-processing way. And then Jeremy mentioned that we shouldn't expect closer systems than 1708-17. So this is, or in the near future. And so we need to do, to analyze them, their angular dependence once we have, the full pipeline of simulations, and that angular distribution will give us an understanding of the priors and a better understanding of what we observe or don't observe from neutron star merger events that LIGO sees. And Manuela pointed out the workshop that she attended that involved a great majority of the observational people involved in multi-messenger transient astrophysics. And Federico said, is there a set of equations of state associated with nice research? We could do a battery of tests, and Jeremy reminded us that there are probably only a couple objects that are constraining the equation of state that Neisser sees. And Neisser, though, does a good job at measuring the compactness and the radius of the neutron stars. So,
all right, thanks, Scott.
Yeah.
I can take the next bullet. It actually looks pretty straightforward. People asked, does anyone have experience evolving hydrostatic tori with tabulated EOSs? And it seems the short answer is it's hard. And the atmosphere in particular is a problem, and I think we saw that a lot yesterday when we were talking about the handoff. You end up getting large transients whenever you have, when your atmosphere is not behaving well. Josh mentioned that Jonah Miller is working on the issue, so we can follow up with him. Seeger and Metzel have started with it, but I guess they started with it. I don't know. They ended up with, right? They were trying to get, I don't know how much, yeah, I don't know what they were trying to do exactly there, but.
Yeah, not all groups start with hydrostationary tori, so we were just trying to figure out which groups did. and that was one of them. But
Okay.
no one from that group was online to discuss how they tested it. So, I'll take the next one. So, this this question was about what is the best optical depth calculator out there. Francois was gracious enough to remind me that they looked at it a little bit. So they compared array by array calculation with the iconal method, and found that the neutrino luminosities matched within 20% level. So not too bad compared to other errors. And then there was some discussion about, well, it became a rather lengthy discussion about radiation transport methods, and then we realized, well, maybe we shouldn't worry about the optical depth calculator because the leakage scheme, which is the only scheme that really uses the optical depth calculator, is the leakage scheme isn't the end all and be all to these kinds of schemes. And then Phil Chang asked, really, what goes into the choice of choosing which method to use, and I described a little bit some of the choices, in particular, different regimes of density make neutrino thin approximations valid, and then there are a couple transport methods, Monte Carlo and Boltzmann, and blast off. And then Manuel asked if there's a way of actually, measuring the performance accuracy of these methods. We went into a great deal of discussion about details and performance issues of Monte Carlo and M1. Leakage is not does not naturally come from the full transport equations, so it's kind of an ad hoc method and is not trustworthy in general, but in certain problems maybe it's fine. And then Josh described a little bit more about their method of characteristics moment closure scheme. And Julian asked some questions about the costs of using multiple frequencies in this regard with respect to that method. We discussed a few regions of validity or invalidity of these methods, and Josh pointed out a few failure conditions or problematic conditions, in particular highly relativistic shocks. And then Julian mentioned that Brooks Kinch is at Lanel, and Josh mentioned that he's helping them implement full Compton into their mock MC code.
So I'm putting 0.5 now back up to 0.3 because it's basically discussing the same stuff. So kind of, I don't know, some of the sub bullets are a little bit out of order, but so let's, I don't know how Google Docs is automating this.
You gotta change the indentation. It's okay, I can fix it.
Okay. Yeah, so we talked more about the Nielsen scheme, which again is basically the optical depth scheme, which is relevant to the leakage scheme, and again, it seems reasonable, and as long as we have an algorithm that works reasonably well for this algorithm or for this for this approach for leakage, then I think we may as well stick with it. Then Josh and I talked a little bit about some a suite of test problems for GR rad hydro. Yeah, I wrote, I'll change that to GR rad hydro because rad MHD is almost to the point where you can't really do quantitative tests. Just I think it gets too noisy. We saw that with the EHT comparison, that you get to the point where you're comparing things at such a rough qualitative level that it's more of a comparison than a test. So this question here is really more about tests. And when I think of a test as something that you compare on a very quantitative level to test codes and algorithms. So of course the point of a good test is something that is not trivial, but it's not too noisy or difficult. So I'd be happy to be involved in getting some nice test problems formulated in the literature. Let's see, so the next bullet here is about the nuclear EOSs. So I'm just going to skip down to the next Monte Carlo. Whoa, that's a long bullet. Let's see. Let's actually move this just for clarity. Let's move the Ruffert bullet. Actually, Scott, maybe you should do this, the editing, because I messed up all the indenting. Can we move 0.5 up to like 0.3 between the current 2 and 3? Perfect. Thank you. Yeah, so Ruffert is the one that calculate the heating and, well, what I actually don't remember what exactly does Ruffert. It's the heating and the cooling and the absorption capacities, all that sort of thing.
Yeah, the composition rate, the electron, leptonization loss rate, lepton number loss rate.
Right. So for that, Ari pointed out that those are based on quantum mechanics calculations, and the big question there is what the chemical potential is, which in turn depends on the equation of state. Here we have a blank, so maybe Francois can jump in. We had we quoted Francois saying uncertainty in, or maybe he was asking a question.
No, he made a point and I couldn't follow it. So
okay, so Francois, if you're still on, you can help clarify that point.
Or we can just remove the line, maybe.
Okay.
There was a comment by Francois in the chat that it's still there before we close. So scroll like.
Let's see.
No, it's gone because I logged out for me.
But I didn't. Let's see. You just said that they used gray versions of the new lib tables that don't have a full comparison to Ruffert. So.
Yeah, so we did talk about opacities that they're kind of uncertain, and there's some debate about whether or not the opacities are important in the merger process because it happens so rapidly. David, though, said, well, the opacity may be important in altering the composition of the wind that is then ejected, that is launched in the funnel wall region. So there's a sharp gradient in density if the system is rotating, if the core is rotating, and the funnel region will be evacuated, but then the wall will have a sharp density gradient, and so the opacities may alter how much the the outflow changes in composition, and so that could affect the late time kilonova signal. Excuse me. And then I was like, okay, well, this is a great discussion, but I really wanted to just make sure our rates are right. And then David said, well, just compare it to the new lib code that Evan O'Connor wrote, and voila. So, but it was actually really good, better discussion than I intended with that question.
Okay, great. So back down to, I guess, point 6 now, again, back to Monte Carlo. What are some of the, I guess, what are some of the important steps forward that we need to do with Monte Carlo transport to apply it into the supercomputer usage, and going to get into these mainstream codes like the Einstein toolkit. I mentioned that on one hand it's trivially parallelizable, but there's the problem of load balancing and overhead. Josh said the same thing, and pointed out that just historically we've had the problem of that a lot of these rad hydro codes start as hydro codes, and may be well balanced in the hydro regime, but then you add in radiation, and that ends up being the biggest computational cost. But of course the code wasn't built around the radiation, it was built around the hydro. So I don't know if there's much we can do about that. I think we're kind of in the same boat, although some of the efforts that Scott and I are working on now with harm and Pandorata, I guess that is the same, because really it's the harm that's the optimized and parallelized version, and forcing Pandorata on top of it is essentially the same as adding radiation, and that we are almost certainly going to be seeing some scaling and load balancing problems. Then the discussion shifted over into question of incorporating GPUs, which a lot of modern architectures include. Are these well suited for Monte Carlo methods? Maybe not as obvious as we would have thought. Josh pointed out that, especially in the Kerr spacetime, that the geodesics are not such a huge computational cost, but in dynamical times, dynamical spacetimes, they could be. Still, again, a lot of the cost is with overhead, and that will certainly be the case when including load balancing. At the same time, pointed out that because the Monte Carlo methods are inherently noisy, that I guess that could be seen as a positive as well as a negative, because they mean that you don't have to be so worried about every other noise source, such as double precision in GPUs. Again, Josh pointed out that Monte Carlo is not as good for GPUs as you might have expected because of the branching, right? GPUs like to just do the same thing over and over again. Josh pointed out the importance in code development of portability rather than optimizing for a particular architecture, and that also is a good way for writing better code. David pointed out that that they're also trying spectral methods in radiation transport, which is problematic when you get to low optical depths. But the spherical harmonic, let's see, I'm trying to recreate this in my mind, right? A spherical harmonic filter, I mean, that's essentially what the spectral methods in radiation transport come down to. And relatively small number of moments I guess, moments / harmonics works. But obviously those don't do well for sharp tests like the shadow test, which actually I think reflects more on the fact that that's not a great test, because right, it's not really appropriate for our types of problems. We're interested in more physical problems where you do have a whole bunch of radiating spheres without huge gradients in the radiation field. Again, talked about some of the benefits of Monte Carlo, the number of particles you need. Where the optical depth is not so good, it's good. Monte Carlo methods are good. Phil raised a question of how important are the true geodesics, especially when the geodesics become time consuming. How important is it that you actually need to use the geodesics versus the straight line approximation? And not surprising, that depends on the optical depth, because how far is the ray going through your problem is very important. Other relativistic effects such as Lorentz invariance, redshift, those may be more important because those certainly add up in a secular way. Even if every step is straight line, you're going to add up a lot of error from the redshift. And maybe not for the TCAN applications, but certainly for other radiation disk problems, these are very important, right? If you're computing iron lines, that's going to be very important. Federico asked, what about modeling neutrino leakage for short evolution? So I'm not sure that this question is best included in this part of the outline, but maybe Federico can clarify this. I'm trying to actually remember this part of the conversation.
Yes, no, I was referring to a previously discussed topic in which the audience said that neutrino leakage seems not to perform well for long dynamical time evolutions, while it can perform well for a short time. So basically, I was asking if one can model a short time, for example, a merger with neutrino leakage, and then pass to a different method if he's interested in performing longer evolution for the remnant, or for the black hole, or for an eventual disk that is forming.
Okay, that sounds fine. So who? Maybe one of the editors can move this the point Q back up to one of the neutrino leakage bullet points. Okay, can I hand it back to you, Scott, for the last point here about Einstein Toolkit?
Sure. Whoops. All right. Sorry.
Or Zach, if he's online.
Yeah. Oh, okay. So now I remember what we were talking about. Okay. So this is about how easy would it be to port Monte Carlo into Einstein Toolkit. Josh said it's tough to say because there's lots of passing of data back and forth between processing units, at least in the way that the Blight code handles the domain decomposition. They do domain decomp the MHT calculation and then pass around the particles based upon where they are. Zach at the end says that he wrote a particle tracer, the particle tracer ET Thorn, and it can evolve populations of particles. He's used it for seeding magnetic field line calculations, and he sees no performance impact up to about 10,000 particles. but it may be able to handle more. Maybe though, people have said, well, we need like millions or tens of millions of particles for a calculation. So there's some sense that maybe this wouldn't be adequate as implemented. Then there was some discussion about some work that has been done specifically for Monte Carlo. David Radice pointed out this paper that's pointed out here. First author is Evgeny Kamalov. That's involved the Caltech group. And they implemented a Monte Carlo scheme and Einstein toolkit. I looked briefly at the paper. It looks like they did a number of 1D tests. I don't know if it was multi-D, but I leave that to the readers or the audience to read that paper. And Francois said that they parallelize their Monte Carlo code pretty well, cell by cell, and found good results. And it didn't significantly impact the performance of their calculation. And that's a wrap.
Okay.
Wonderful. Can we stop the recording?